Now, it does turn out that this subtractive nature of light is kind of more useful, even though I think it's easier conceptually to add colors together. But if you think about when we were looking at that rose on one of the first slides, what we were actually looking at was the subtractive nature of light. Most of the things we look at are not light sources. Most of the things that we see are illuminated by something, say something like a sun or something like a light bulb that's going to put off all the colors of the rainbow. What reflection does is reflection is going to take away some of the incident light. So it's going to start off with red, and what colors does it remove? So suppose, for example, we were looking at a daffodil, and we all know that daffodils are going to be yellow. So suppose we had some white light, and that white light was showing on a daffodil. It's my poor attempt at drawing a daffodil. It's going to be yellow. Well, what is yellow exactly? Well, where I finished off the last slide with is I said, well, yellow is actually going to be the absence of blue. So suppose I had some white light on my daffodil, so here I have my daffodil, and what's going to happen is it's going to take away blue, essentially. So we're going to have some pigment or something that's going to absorb some of that blue, and if I initially had my red plus my blue plus my green, then this would be my white light. But when I go ahead and I say, well, let me just go ahead and take away this blue, well, I'm going to mix together my reds plus my greens, and if you go back to that color wheel, then I'm going to have an object that appears to be yellow. So let's kind of come back and ask ourselves, the question, if we had a blue object, when's it going to appear black? And this is kind of like when that ball that was red appeared black when I shined some green light on it. Here I have my object, and this object is going to be blue. And what we could say is we could say yellow light, this light right here, is going to be the absence of blue. So if I had a blue object and I shined yellow light on it, then the blue object is going to appear black. Why is that? Well, blue wouldn't have any, or an object that was blue isn't going to have anything to reflect back at us. So, kind of coming back to our color wheel, we can go ahead and say standard thing, red plus blue is magenta, yellow, cyan, all these good things. And we could say yellow is the absence of blue, we could say magenta is the absence of green, and cyan is the absence of red. So we can think about these kind of subtractively. Suppose we were to shine three colored lights on something, a red and a blue and a green, and we were to shine this thing onto a golf ball. So here I have my light shining in that direction, and there you go, that direction, and that direction. You can kind of see that here we have the absence, and here we have the absence, and here we have the absence. And magenta is going to be the absence of green. You can kind of see that guy just right here. You can see cyan is going to be the absence of red, and we can see the yellow is going to be the absence of blue. So looking in the shadows is going to allow us to see the subtractive nature of light. Now, we could even go ahead and talk about how subtractive colors are kind of complementary to the additive primary colors. So if we were to, for example, take magenta plus green, well, magenta is going to be the absence of green, so you add those guys together, and we're going to get our white light. Similarly, yellow is going to be the absence of blue. You add those together, and we're going to get white light, which is red plus green plus blue. An example of this is going to be kind of color printing. And whenever we print colors, actually we print the subtractive colors because we're looking at the reflection, we're looking at the absorption of it. So suppose I were to go ahead and take a look at printing a photograph, and here I'm going to print the subtractive colors. I'm going to print the magentas, I'm going to print the yellows, and I'm going to print the cyans. When we go ahead and we put all these guys together, we might get a picture that looks like this. Then we add some black and white to give it some contrast, and we're going to get our finished result, which is going to look like that. Now, just a quick little check your neighbor question. Suppose we had a red rose. When's it not going to appear red? So there's my red rose. Looks an awful lot like my daffodil, but that's okay. Well, if I shined red light on it, then it definitely is going to have some red to reflect, and our eyes would definitely perceive some red. Orange is actually going to have some red built into it. It's going to be mostly red and a little bit of yellow. White light definitely has red in it. It's going to have red plus green plus blue. Cyan does not have any red light in it, and so the red rose is not going to appear red when it's illuminated by cyan. Now, lastly, I want to really quickly talk about mixing different colored pigments. Suppose we wanted to talk about white light. White light's going to be all the colors of the rainbow. Red is going to be primarily red, maybe some orange mixed in. Green's going to be kind of this smear right here, and blue is going to be this smear. Yellow is going to have a whole bunch of colors in it, these colors right here, but it's missing the blues. Cyan is going to be missing the reds, and magenta is going to be missing the greens. Now, if we were to go ahead and think about this in the language of subtraction, suppose I had a yellow filter, a magenta filter, and a cyan filter. Well, here I'm going to see cyan, here I'm going to see magenta, and here I'm going to see yellow. And where these guys overlap, we're actually going to start to see some of the primary colors. We're going to see our blues, we're going to see our reds, and we're going to see our greens. Where no light can make it through, we're going to absorb all of the light, and we're going to essentially see our blacks. Now I kind of want to change gears, and I want to talk about why is the sky blue, why is the sunset red, and before I do that, I want to say what can light do when it interacts with matter. Well, it has a couple of choices. It can be absorbed, and when it's absorbed, the energy goes into the medium, and it's going to warm it up. It could be reflected, and when it's reflected, what's going to happen is it's going to bounce primarily in the backwards direction, and the light's going to go back to the source. So if I had some light coming in to this medium right here and it's absorbed, then it's going to go into it. Here I can have reflection where the light comes in and the light bounces back, usually in the backwards direction. And the light could also be scattered. And when it is scattered, then what's going to happen is I could have my light kind of coming in, and scattered kind of implies any direction. So the light could go in that direction, it could go in this direction, it could be reflected in the backwards direction, it could go in that direction, or it could go in that direction. Bear in mind, when it's absorbed, the energy goes into it. When it's reflected, it goes back to the source. When it's scattered, it can pretty much go in any direction. Now, I want to talk about one very special type of scattering. This is actually called Rayleigh scattering. And what happens with Rayleigh scattering is we're going to say that we're going to have some light and it's incident upon something. And in this case, it's going to be the molecules in the air. Now, these molecules are very, very, very small. And I've talked about how small they are. They're much smaller than the wavelength of light. And because they are so small, what they're going to do is they're preferentially going to scatter, and they're not going to scatter all wavelengths equally. They're going to scatter the short wavelengths more preferentially than the long wavelengths. Now, if we think back to our good old friend Roy G. Blue, Indigo, Violet, the sun's not going to put off enough violet for us to be able to see, so we're primarily going to see a blue sky. So here I have the sun. The sun's putting off all the colors of the rainbow, and here I have these teeny tiny air molecules, and they are preferentially scattering the blue light. When you look up at the sky, what you're going to see is you're essentially going to see blue light. The reason for that is because air molecules are small, and they're preferentially going to scatter the blue light, less so the longer wavelengths. Now this little simulation photograph right here kind of shows what I said in maybe a better picture form. Here we're going to have our white light, and it's going to come in, and it's going to scatter off something that is very, very, very small. And what's going to happen is you can kind of see the blue light coming off here, the blue light coming off here. And so all the blue light is scattered. You also see it here and here. And the red light, not really affected so much. And that's pretty much the basis for Rayleigh scattering. Again, it's going to be the preferential scattering of the small or the shorter wavelengths, not so much of the long wavelengths. It essentially has to do with the size of the air molecules. They are much, much, much smaller than the wavelength of light, and they're going to preferentially scatter the short one. Now, if you were to think about this, if you were in the ocean, then you're going to be much smaller than the waves that are around you, and they're not going to bounce off of you. Why is that? Well, the waves are much longer than what your body is, so it's not going to splash back, if you will. If, however, you were to go into a hot tub or a bathtub and you were to splash around a little bit, then the wavelengths are much shorter than your body. So how long the wavelength is relative to what it's trying to scatter off of is going to make a difference. Now, if we were to talk about aerosol particles, and another word for this could be something like pollution, then it turns out that aerosol particles are much larger than the wavelength of light. And we could say that it's going to be about 2.5 to about 10 micrometers or so. And micro is times 10 to the negative 6. Bear in mind that visible light, we're talking about 400 to 700 nanometers. So pollution is much larger than light, and so it's going to scatter all wavelengths kind of equally. So if we were to look at the sky on a day where there's lots of pollution, up here we're going to see lots of blue. Down here it looks more whitish. The reason for that is because here we have the pollution. We're going to have scattering of all wavelengths. Up here, above all this stuff, not lots of pollution way up there, so we're going to primarily scatter our blue. Now, if we were to, for a second, take a look at our nation's capital, and it's going to look very different if you look at it in the winter versus the summer. And I can look at this photograph and I can tell you right here that this is very white. It's not very blue. The reason for that is because in the summertime we tend to have lots of pollution, we tend to have lots of humidity that makes that pollution swell up, and what we're going to see is we're going to see a skyline that is primarily white, and we're not going to be able to see that far. If this photograph was taken in the fall or the winter time, then it's going to look a whole lot bluer than it does right here. Now this kind of says everything that I said, but now you kind of have it in text form. Why is the sky blue? Well, the small air molecules scatter the small wavelengths more than the big wavelengths. Again, this is called selective scattering. We're selectively going to scatter the blue. And as I mentioned, kind of humidity matters. If we had a clear, dry day, not a lot of pollution, then we're not going to have a lot of scattering of the longer wavelengths. We're going to see a deep blue sky. Even if it's humidity, it's going to be a beautiful blue sky, maybe not as deep. But once we start to put some stuff in there, like dust or smoke or something like that, then it's going to be less blue and it's going to be more whitish. And it does turn out that rainstorms tend to wash away some of the stuff in the air, and we get our deep blue sky back. Now, how come the sunsets are red? And here we have a picture of a nice, beautiful sunset. So let's talk about that a little bit. Now, I kind of talked about why the sky is blue, and I said that was due to all the stuff in the sky. So here's all my stuff, and at noon, well, the sky is going to look relatively blue, and the sun's going to look relatively white or yellow or greenish. And if, however, I were to go ahead and talk about what happens at sunset, well, at sunset, here we have our white light, and it's going through all the stuff, all the stuff, all the stuff. Well, all of the blue light is being scattered away and scattered away and scattered away. And here I am at sunset. Well, what's going to happen is all the blue has been scattered away. And what I'm left with is I'm essentially left with more or less red light. And that's why the sunset is going to look red. All the blue has been scattered away by all the stuff. And if I were to even go ahead and put more pollution in the atmosphere, then more pollution in the atmosphere means that my light's not going to take a straight line. It's actually going to bounce around, bounce around, bounce around. The more it bounces around, the more blue gets scattered away, and the redder my sunset appears, and the more beautiful it is. Now this just pretty much says everything that I said on the previous slide, but now you kind of have it in text form. So if we were to go ahead and take a look at the sun's putting off all the colors. You take a look at that, and you're going to see a yellowish thing. If you were to look up later on, then what you're going to see is you're going to look up at the sky. The sky is going to appear to be blue because all this stuff is scattering away the blue. Again, preferentially scattering the short wavelengths. And when we're right here, it goes through the atmosphere the most. Most of the blue has been scattered away, and we're going to see the long wavelengths, or the low frequencies. We're going to see the reds, we're going to see the oranges, and we're going to see the yellows, kind of the ROY of the Roy G. Biv, if you will. Now, if we were to go to the moon, how come the Earth isn't red tinged? Well, it turns out that if we go to the moon, we need to wear spacesuits, and we need to wear spacesuits that also have oxygen and stuff like that. The moon does not have an atmosphere like the Earth does, and it doesn't have anything to do any scattering away. So the Earth is not red tinged because there's nothing to do any scattering, or there's not a lot to do the scattering. Is the night sky blue? Why yes it is. It's just too dim for us to perceive because, well, the moon doesn't light it up very well. If we were to look at a time exposure, then take a look right here. It does look blue to me, and what's going on is we're not getting rid of the atmosphere, and it's the atmosphere, those small particles that preferentially scatter the blue light. We're not getting rid of that at night. Now, how come clouds are white? Well, clouds are white pretty much for the same reason the aerosol and pollution is going to be whitish. Clouds are going to be very, very, very big droplets, and they're going to be big droplets primarily of water with some usually pollution in the middle of them. And what we're going to do is we're going to scatter all the wavelengths. So because it's so big compared to the wavelength of light, we're going to scatter the reds, we're going to scatter the greens, we're going to scatter the blues, and we're going to essentially scatter all of these guys equally. And I don't know about you all, but if I mix red plus green plus blue, then I'm going to get white. And that's primarily why clouds are white. Now, I'll finish off by saying, why is water kind of a greenish blue color? Well, it turns out that water molecules are going to absorb primarily red. They're not so much going to absorb the greens and the blues. And if we think back to it, white is going to be red plus green plus blue. And if we were to go ahead and absorb that red selectively, we're going to be left with the greens and the blues. And you can kind of see a greenish blue right here. So red is going to die off very quickly in water, hence a greenish-bluish color for water. Interestingly enough, if we were to go to somewhere where there's lots of stuff in the water, like the Rockies, then we're going to have sunlight, and it's going to come down, and again it's going to be white light. It goes into the water, and the water is primarily going to absorb the red. But in the Rockies, there's lots of stuff in the water. And much like if there's lots of stuff in the air that scattered away lots of blue light, the sunset was red. However, now we have our white light, and it's going through the water, and it's going to scatter away all the red. So what's going to happen is we're going to have a longer path length as the stuff bounces around and then eventually comes out. And what's going to happen is a more vivid blue and a more vivid green than if there wasn't a long path length to scatter away or to absorb all of the red.